Number Theory, Section 3, Congruences and Modular Arithmetic. Video 6, Wilson's Theorem. Wilson's theorem states that n is prime if and only if n minus 1 factorial is congruent to negative 1 mod n. Now, two things to notice here. First of all, we've got an if and only if theorem, so it goes both ways. And secondly, you might be a little bit surprised by this minus 1 mod n just here. Everything that we've done so far, we've been considering things between 0 and n mod n. But here we've got negative 1. This is just a shorthand for writing n minus 1 mod n. So let's have a look at an example then. Take n equals 7. 7 is prime. If I work out 6 factorial, I get 720. And 720 is 103 multiplied by 7 minus 1. So that is 6 factorial is 1 less than a multiple of 7. 6 factorial is congruent to negative 1 mod n, which satisfies what we have here. If n is prime, n minus 1 factorial is congruent to negative 1 mod n. However, if we take n equals 10, which is composite, and work out 9 factorial, we get this number here, which you can see ends in a 0, so we know straight away it must be a multiple of 10. So it's congruent to 0 mod 10. So we've got something which is not prime, and n minus 1 factorial is not congruent to negative 1 mod n. Now, as with Fermat's little theorem and Euler's theorem, you don't need to know a proof of Wilson's theorem for the course, but you might find that looking at an outline of a proof will give you some useful insights and help you to understand the proof a bit better. Let's start by thinking of what happens when n is composite. So when n is composite, I need to show that I'm not going to get something that's congruent to negative 1 mod n when I work out n minus 1 factorial. But if I think about n as a composite number, that means that it must be the product of some two numbers a and b. It must have a factor pair a and b, where a and b are less than n. Now I need to be careful here, because if n was the square of prime, then my factor pair would be p times p, and my argument wouldn't work. I'd need to change it slightly. However, assuming that a and b are distinct, I now have that in n minus 1 factorial, I would have 1 times 2 times 3 and so on. Somewhere in my factorial, I'm going to have an a, and somewhere I'm going to have a b. So I know that when I multiply all of these together, I've got a times b, which is a multiple of n. So n minus 1 factorial, in this case, is going to be congruent to 0 mod n, just like we saw with n equals 10 before. You might like to think about how you can adapt this argument for the case where n is the square of a prime, and you might need to think about the case where n is 4 separately, because that's a little bit different. Okay, so what if n is prime then? Well, let's take an example of n equals 11 and see the outline of the argument. So when n equals 11, then my 10 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And the neat trick that we can do here is we can pair these off into things that give 1 mod 11. So if I work out 9 times 5, I get 45, which is congruent to 1 mod 11. And similarly, if I work out 8 times 7, I get 56, 1 more than 55. If I work out 6 times 2, I get 12, which is 1 more than 11. If I do 3 times 4, I also get 12, which is 1 more than 11. So all of these things multiplied together is going to give me 1 mod 11. The only way that I get away from that 1 mod 11 is when I do 1 times 10, which gives me 10 mod 11. 10 is just the same as minus 1 mod 11. So my prime number is congruent. My prime number, when I take away 1 and find the factorial, I get something that is congruent to minus 1 mod 11. Let's see that written out neatly. So the statement of Wilson's theorem, n is prime if and only if n minus 1 factorial is congruent to minus 1 mod n. Our argument, if n is composite, is to find the factor pair that is in n minus 1 factorial, adjusting that slightly if I've got the square of a prime. So that means that I'm getting 0 mod n, so it's not congruent to minus 1 mod n. If n is prime, we can pair off the factors in n minus 1 factorial so that I get pairs of factors which have a product of 1 mod n and just leaving behind 1 and n minus 1. So we saw it with 11. We had 9 times 5, 8 times 7, 6 times 2 and 3 times 4 all gave us something congruent to 1 mod 11, leaving behind just our 1 times 10. In this video, you've learned Wilson's theorem and you've seen an outline of how to prove Wilson's theorem.